So you think you know how to take the limit. You know L'Hopital's rule, you know the squeeze theorem, you know all these techniques for taking the limit. But what even is a limit? So today we're going to talk about the epsilon-delta definition of a limit. It looks like this, it's written like that, has a lot of symbols, has a lot of math jargon, but we'll unpack it today. So it says that the limit as x goes to a of f of x is equal to L if and only if for all epsilon greater than 0 there exists delta greater than 0 such that the absolute value of f of x minus L is less than that epsilon whenever the absolute value of x minus a is between 0 and delta. Okay, a lot to unpack there. Let's think about this. Well, remember, this is the definition of the limit. It's to take what we know in common terms and turn it into mathematical terms. So in common terms, we're saying near a, f gets really close to L. So near the value that x is approaching, the output values get really close to what I think the limit is going to be. Okay, so it turns out all these components are right here. They're just a little hidden. Let's look at this part. Near a. Near a. Oh, it's this part right here. So what is this saying? The absolute value of x minus a, or the distance from x to a, is less than delta. In other words, well, x is near a. Let's look at this next part. F gets really close to L. Well, that corresponds to this part here, where f of x minus L is less than epsilon. And the idea is epsilon and delta, they're probably going to be really small numbers because when we talk about the limit, we talk about getting closer and closer. Here's how I like to think about this definition with the epsilons and the deltas. Imagine there's a skeptic, and I say, okay, you know what? The limit as x goes to a of f of x is equal to L. And the skeptic looks at me and he says, or he or she says, I don't know about that. I don't believe you. So they say, okay, prove it to me. Let's say epsilon is equal to 0.01. In other words, we're saying all the values of f are within a 0.01 of L. The distance from f of x to what we claim the limit value is going to be 0.01 at most. Well, if the limit really does exist, I should be able to respond. I should be able to say, okay, I got an answer for you. Delta equals 0.5. I have an answer for you. All the values of x within a delta of a, or within 0.5 of a, are going to give me output values that are within 0.01 of L. I think it helps to look at some counterexamples to explain why this definition here is necessary. Okay. Let's take a look at this example. It's a piecewise function. Namely, on the left of 1, it's going to be x squared, and on the right of 1, it's going to be x plus 1/2. All right. What to do? Okay, so let's claim that the limit as x goes to 1 is 1. That'd be a reasonable guess. It looks like it goes to 1, at least on the left-hand side. Well, our skeptic over here, our skeptic's going to try to disprove us by giving us a challenge, by giving us an epsilon. So let's say, okay, can you get all the, let's say epsilon equals 2, says the challenger. They say, can you get all outputs of the function to be within 2 of 1? In other words, we'd really like for all the values of f of x to be between -1 and 3. If we can do that, we're doing pretty good so far. Okay, let's try it out. What if I choose delta? So what if I restrict my x values to be within 1 of 1? In other words, I'm choosing my x values to be between 0 and 2. And if you look carefully, well, we did it, didn't we? Look at all the output values. The lowest value we get, that's definitely greater than -1. The largest value we get, it turns out that's also less than 3. All the values of our function are pretty close to L, but we want to say we get really close to L. So our challenger goes again, they say, okay, you got me there, but what if epsilon is equal to 0.01? I say, okay, let's try it. Maybe I can do it. What if I choose delta to be smaller? I don't think I can do it, because no matter what delta I pick, notice that I can't get all the values of the function to be within 0.01 of 1. So the goal now, right, after they gave the challenge, the goal was to get all the values of the function within 0.01. In other words, get it between 0.99 and 1.01. And I'm trying my best. I'm looking at all the values near A. I'm looking at all the values near 1. I'm getting as close as possible, but somehow I can't do it because of this leap here. Because I'm always going to include some values that are actually more than 0.5 away from 1. So now it sort of makes sense why this definition is necessary. Because it's taking what we have, it's taking the challenge and saying, if the limit doesn't exist, that means there is some challenge that's going to beat me. There is some epsilon for which I can't find a delta. There is some neighborhood around A for which the values of f don't get really close to L. And if the values of f don't get really close to L, well, then the limit doesn't exist. Or at least the limit's not equal to L, rather. So let's look at an example where the limit does exist, and maybe it'll start to make some sense. It's this one right here. It's not too important exactly what the function is, but we have the point 5, 4, and around it looks continuous, and it is continuous. So, challenge, limit as x goes to 5 f of x. We're going to try to show that it's equal to 4, and we'll see if the skeptic can beat us here. So, the skeptic says, okay, that's your claim, really? Well, I'm going to say epsilon equals 1. Can you get all the values of the function within 1? And I say, I think I can. Let's try this. That looks pretty good to me. All the values that I had there, all the outputs, they're within 1 of 4. As in, they're between 3 and 5. The skeptic goes again, they say, you got me there. What if epsilon is equal to 0.001? Okay, you can imagine I zoom in really, really close. I do the same thing, and it does look like in some neighborhood around, all the values are within 0.01. As in, they are really close to 4. And the skeptic does this again and again. They give smaller and smaller epsilon, but every single time I can find delta. This is what we're saying here. For all epsilon, there exists delta such that this condition holds true. As in, we can beat the skeptic, or the skeptic can't beat us, which means the limit does exist and is equal to 4. This statement is true because the skeptic can't beat us. So that's the idea. The idea is really what we already know about limits, but written formally. So we want the definition of the limit to be so that near A, f gets really close to L, and that's what epsilon-delta allows us to accomplish using this idea of a challenger and me trying to find that delta, trying to find that neighborhood.